Hi guys, I wanted to just do a quick recording of the week 9 homework, and I realize that it's due tomorrow, but some of you have reached out and I apologize this week for the slight delay. On question 1, I have it on the back here, it just asks you, actually let me flip it again so we can read it, to write equations that show NH3 as both a conjugate acid and a conjugate base. And remember, this is specifically within the context of the Bronsted-Lowry acid and bases, but the conjugate base is basically what's left after the acid species donates its hydrogen. So here, right, we started with NH3. Now, this would be the equation where NH3 is serving as a base, right? Because we have NH4 plus OH negative, okay? So this is gonna be the acid. It donates the H to this, creating water. So this is what's left. It's the conjugate here. NH3 serves as a conjugate base. Here, the conjugate acid, right, what would remain after accepting a hydrogen. So here, the NH2 adds on a hydrogen to become NH3. So in this equation, NH3 is a conjugate acid. It results from hydration of that. Now, in this set, I want to apologize to you guys because once again, unlike here where I copied and pasted a screenshot, I screwed up several times, including here where it should have been SO4 subscript and then the superscript minus. Same thing here with the 3 and here with the 2. So my deepest apologies for this. What I tried to do, oh no, I'm sorry, it's over here now, is just show you some of these, right? So basically, the conjugate acid we've already established would be what results, and that's what I put over here, when you add a hydrogen. And you have to remember when you're dealing with the charge, with the sign, the plus or minus, that each hydrogen atom contains one proton but no electrons, right? No hydrogen species have any electrons. So addition of a hydrogen atom is always going to add one positive charge. And oppositely, the conjugate base is what results when you take away a hydrogen, and therefore you take away one positive charge, or AKA it becomes one charge more negative. So if we start with OH minus, the conjugate acid, remember, would be what results if you add a hydrogen, so H2O, and that we lose the minus because we added a positively charged H. The conjugate base would be what results when you lose another hydrogen, so OH2 minus, right, because you're losing one positive H, so it becomes two negative charges. Same thing here, H2O, you add a hydrogen, H3O plus because we've gained a positive hydrogen. This is the conjugate base when we lose an H and lose a positive charge. For number 3, they ask you to identify and label the Bronsted-Lowry acid, its conjugate base, and then the Bronsted-Lowry base and its conjugate acid. So, okay, what I tried to show you with the first example, here's the original equation, HNO3 plus H2O yields H3O plus NO3 minus. Okay, so the Bronsted-Lowry acid is the species that's capable of donating a proton. So which one donated the proton? The HNO3. The conjugate base of the Bronsted-Lowry acid would be the species that results when this loses an H, which becomes, excuse me, right here, conjugate base, right? So these go together. This is the Bronsted-Lowry acid and the conjugate base. Here's the Bronsted-Lowry base, the one that accepts a hydrogen, and here's the conjugate acid, what this guy looks like after it takes on an H. Okay, and then finally, we have the last question, question 4, which says the ionization constant for water, Kw, is 9.311 times 10 to the minus 14th at 60 degrees Celsius. We don't actually even need to worry about 60 degrees Celsius for this. What we're asking for is to find the concentration of hydronium ion, hydroxide ions, the pH and the pOH for pure water at 60 degrees Celsius. Okay, so the equation, right, we know Kw, we already know that. They gave it to us, 9.311 times 10 to the negative 14th. for water, because they state that we're dealing with water, the concentration of hydrogen ions is always going to equal the concentration of hydroxide. Why? Because when H2O splits, these are the two species that remain. So you can rewrite this to be Kw equals the concentration of hydrogen ions, right? You could just as easily write that one, but we're going to use hydrogen ions squared. So Kw, we already know, is 9.311 times 10 to the negative 14th equals the H plus concentration squared. How do we get rid of the squared? We take the square root, okay? So if you take the square root of 9.311 times 10 to the negative 14th, we get 3.04 times 10 to the negative 7th. Since the concentration of hydrogen ions equals the concentration of hydroxide ions when we're dealing with water, then we can use the concentration of hydrogen ions to calculate pH from here. So now we know. It asks you to calculate the concentration of the hydronium, hydroxide, and hydrogen, which we did. Okay, these are the concentrations, 3.04 times 10 to the negative 7th, individual ions of each of these. Then we can use this, the concentration of hydrogen ions, to calculate pH. So we take the negative log of the concentration of hydrogen ions, excuse my dog over there, which is 3.04 times 10 to the negative 7th. Take the negative log of that, which equals 6.52. So both the pH, and because the H and the OH are going to be in equal quantities here, the POH equals 6.52.